All right. This video will be solutions to homework problems from section 5.6. Section 5.6 is integration by parts. So I'll do a selection of problems and hopefully that'll answer any questions you have and help you assimilate the material and solve the rest of the homework problems. So I'll start with number 4. The integral of x e to the minus x dx. Now our approach to solving integration by parts problems is, remember the formula. The formula is uv minus the integral of v du, and that is equal to the integral of u dv. This is the integral that we're given. This is the integral that we change it to, i.e., this is the integral that we can solve. Our goal here is to take an integral that we're given and turn it into a product minus an integral that we can solve. And that's the technique of integration by parts. Our approach is to determine what is going to be our choice for u, which of these two factors is going to be u, and then whichever one's not u, the other is going to be dv. Now, typically, we want to take, if we have something like x squared, x to the 4th, a power of x, we want that to be u. So we'll try that. We'll say we're going to let u equal x. Therefore, dv is going to be e to the minus x dx. Now, when we look at our formula, we need to know u, we have that, it's x, but we also need to know v. We don't have v. Remember, we're going to find v. We're going to find v by integrating dv, right? We're going to integrate this side and integrate this side. That's going to get us v, and then the integral of e to the minus x will be our value for v. The goal here, of course, is to choose this dv to be something that you can integrate. It makes no sense, knowing that you're going to have to integrate it to solve the problem, to pick something to be dv that you cannot find the integral of. Now, in section 5.5, we learned how to do u subs. Back in Calc 1, we would have integrated this with a u sub. And so we'll move over here real quick. Typically, we're not going to do this with a u sub and an integral like this. We'll typically just do it straight, but we'll do this one with the u sub. We would have said, you know, u equals minus x, du equals minus dx. And we would have said to ourselves, well, we need a negative sign there. And since we need a negative sign, we can introduce it. We're going to multiply by -1, but to balance that, we're going to have to multiply by -1 outside. So this would become minus the integral. That would be e to the minus x, so that would turn into e to the u, and minus dx is du. The integral of e to the u, of course, is e to the u. And so then we would resubstitute, and we would say, all right, that's minus e to the minus x plus c. So the integral of e to the minus x is minus e to the minus x. We can after this, we'll be able to do this in our head because we can think about it. Just do the u sub in your head and think, well, u is going to be minus x. I'm going to take the derivative of that. That's going to introduce a minus sign. So when we integrate this, we get minus e to the minus x. U is x, but we also need du. So we're going to take the derivative of x. That's simply going to be dx. Now that we've done that, now we can solve our integral using parts. So we have the integral of x e to the minus x dx. That's going to be uv minus the integral of v du. I would suggest you write it like this every time and then just fill in the blanks. So this is going to be equals to u, which is x, D is minus e to the minus x minus the integral of v, which is minus e to the minus x. So those two negatives make a positive. And then du, which is dx. So what do we have now? Minus e to the minus x times x is minus x e to the minus x. We just did this integral right here using u sub, or we did it here in our heads. We know the integral of e to the minus x is minus e to the minus x. And then we add our constant plus c, and we're done with number 4. We can leave our answer like this. We can factor it if you like, right? We could take out a negative e to the minus x. That negative sign has now been factored out. That e to the minus x has been factored out, so that leaves me an x. We've taken out negative e to the minus x. That would be plus 1, and then plus our constant. So if you look at the back of the book and the answer is actually factored, you can factor to get the answer that's in the back. All right, so that's number 4. Now we'll skip down and we'll do number 8. Number 8 is the integral of x squared cosine of mx dx. Again, our game here is to do integration by parts because the instructions just say evaluate the integral, but we know we're in the integration by parts section, so we're going to try that first. Besides, we don't have much else at our disposal other than integration by parts. So our goal is to determine u and to determine dv. Again, we have a power of x, so we're going to let that be u. dv is going to be cosine of mx dx. Now we're going to have to integrate that. And again, we're going to have to integrate that using a u substitution, because while we know the integral of cosine x is sine x, we probably should know the integral of cosine mx, and we probably should be able to do that in our head, but it's been a while since we looked at section 5.6. So we'll come over here and we'll do that integral off to the side, and we'll use a u substitution to do it from section 5.5. So the integral of cosine mx dx, and we'll do a u sub. We'll let u equal mx. Then du is going to be the derivative of this, which is going to be m dx. And we'll look at our integral here and we'll think to ourselves, okay, I need this integral. When I do this integral, I'm going to have the integral, I'm going to have cosine, I'm going to have mx, but I need a factor of m in front of my dx. So I can substitute that and turn it into du. But if I multiply by m inside my integral, I'm going to have to divide by m outside my integral, because remember, m is just a constant. Now that allows me to rewrite this as 1 over m, the integral. This is u, this is du, and I have cosine of u du. Well, that becomes 1 over m. The integral of cosine u is sine u is mx. And so our integral of cosine mx turns out to be 1 over m sine mx. So when we find v here, we get 1 over m sine of mx. To get du, we take the derivative, right? Derivative of x squared, and we get 2x. And now we're ready to expand this. This is going to give us the integral of x squared cosine mx dx is equal to uv minus the integral of v du. And if we substitute everybody in here, u times v, that's going to be x squared times v, so we're going to get x squared 1 over m sine mx minus the integral of v du. The integral of v du is going to be, if we're going to multiply these two together, right? V times du. So we're going to have 2 over m. That's just a constant. We'll move that out front. X sine mx dx. The dx comes from the derivative right here, x squared. It's 2x dx. I forgot to write that part down. So now we're left with this integral that we're going to have to simplify. This is done, right? We're done here. There's no more work here. We have x squared over m sine of mx. If we simplify this, the 2 over m is a constant. We can pull that out. And then we have x sine mx dx. Well, that's an integration by parts problem, right? Because we have x times sine mx dx. So that's going to be integration by parts. So what is that going to look like when I'm done? Well, I'm going to have to do a separate problem. I'll change colors here. I'll change from black to blue. And so we'll now work out this using an integration by parts approach. We have u. U is going to be x. We have dv. dv is going to be sine mx dx. We know the derivative of this du is going to be dx. Here, right, we need to integrate sine mx dx. Well, we integrated cosine mx dx, and we got 1 over m sine mx dx. So this is exactly the same structurally as the integral of cosine mx. It's just sine mx. So it's, I hope, clear that that's going to turn out to be 1 over m. The integral of sine is going to be negative cosine. So we're going to put a minus here. And we're going to get cosine mx. And now we're ready to finish our problem. We have to do a u sub, sorry, pardon me. We have to do an integration by parts right here. And we have it all set up right here. So if we complete that, we're going to have from here, right, from this line, we're going to have x squared over m sine mx minus, now don't lose this factor of 2 over m times, and remember, we're doing integration by parts, so we get u times v, but of course it's this u and this v, so that's going to be negative x over m cosine mx minus the integral of v du. So that's going to be minus 1 over m cosine mx. We're going to have to erase this to make some room. Dx. And we close our grouping symbol because we still have this factor of negative 2 over m. Now, if we clean all this up, this stays x squared over m sine mx. Negative times negative, that's going to give me plus 2x over m squared cosine mx. This minus 1 over m is a constant, so that's going to come outside this integral. That negative times that negative is going to make a positive, but don't forget we have a negative out here, so this is going to be minus. This is going to be 2 times 1, that's going to be 2. M times m, that's going to be m squared. And then we have to integrate cosine mx. Well, we've already integrated cosine mx. We integrated cosine mx right back here. So we know what that integral is going to be. The integral of cosine mx, remember we put the minus 1 over n out front because it's a constant. So we integrate this factor, or this integrand of cosine mx. That's going to give us 1 over m. So that's going to give us 1 over m times the sine of mx plus our constant of integration. And so what we really have here, of course, is 2 divided by m cubed. Now, if we take a look at this answer, it feels like it should be correct. And what do I mean by that? Well, we've negotiated our way through a calculus book, 5 chapters of a calculus book. There's some things that we can begin to expect and think to ourselves, well, that makes sense. Whether it means it's right or whether it means it's wrong is immaterial. What I'm saying is it's an inherent idea that we need to develop. We need to develop a feel for our answers. If we look at this answer, there's an x squared, and the m has a power of 1. So power of 2, second degree, power of 1. Here the power goes down. Power is 1, but the power of the m went up by 1. So they changed by 1. Here, x is to the 0 power, but m is cubed. So m went from m to the first, m to the second, m cubed. Okay, that feels good. At least there's some kind of process there. I don't want to say it's a pattern, but it's process. And then we went x squared. We went 2x, which happens to be the derivative of x squared. And then we went 2 here, which happens to be the derivative of 2x. Here we went from sine to cosine. And then we went from cosine to negative sine. So this feels like what we're working on is making sense. Now, whether that means we got the problem right or we got the problem wrong, that's up for the back of the book to let us know. But we want to start investigating in our answers and thinking about, instead of just being a bunch of things we wrote down on paper, we want to look at that and ask ourselves, well, how do I feel about that? On an exam or some kind of an assessment, when we don't have an answer, this kind of behavior is going to lead us to believe, it's going to give us some level of confidence in what we're doing. Okay, so those are the first 2 problems I'm going to work on. I worked on 4, and I worked on 8. Okay, let me clean off the whiteboard here, and we'll do another one. All right, now that I've cleaned off the whiteboard, let's do another problem. So we did 4, we did 8. Let's take a look at problem, skip a couple of down here. We'll take a look at problem 13. Problem 13 is the integral of e to the 2 theta sine 3 theta d theta. Okay, so we looked at a problem like this in the lecture. It doesn't have an x to a power. What we said when we did this kind of problem in the lecture is, all right, one of these doesn't scream take my derivative, and one of these doesn't scream take my integral. So we can go with whichever route we want to go, right? We can try to let u be e to the 2 theta, for example, and we can let dv equal sine of 3 theta, d theta. Now, if for some reason this doesn't work, that's not the end of the world. We'll just start over. We'll erase this. We'll let u be sine of 3 theta, and we'll let dv be e to the 2 theta d theta, and we'll go from there. Sometimes we don't pick them correctly. Sometimes we pick them correctly on the first try. Sometimes we don't. In this case, I'm pretty sure we could go either way and it's going to work. And we did an example like this, and there's an example like this in the reading. So let's go ahead and move from here. We take the derivative of e to the 2 theta. Now the derivative of e to the 2 theta, we're going to have to use the chain rule there. So that's going to be, first of all, e to the 2 theta. Then we have to take the derivative of the inside function. The derivative of 2 theta is 2. And then we get d theta. So we get here 2 e to the 2 theta d theta. That's our du. Now we have to integrate sine 3 theta. Now Stuart just gave us a problem, and we just worked on a problem where we integrated sine of mx. It wasn't a 3, it was an m, and we integrated sine mx dx. And for that integral, we got minus 1 over m cosine of mx. So perhaps the reason Stuart gave us problem 8, asked us to find the integral of sine mx, was so that in the future, when we worked on something like the sine of 3 theta, we could avoid a u substitution step, and we could just do the integral straight up, knowing that we just worked out the formula on a previous problem. So we know if we integrate sine of 3 theta, this is just m is 3. We're going to get minus 1/3 cosine 3 theta. And now we can proceed with our first step for solving this problem. We have the integral of e to the 2 theta sine 3 theta d theta. That's going to be uv minus the integral of v du. And we can read those off our chart. U is e to the 2 theta. V is minus 1/3 cosine 3 theta. So that's going to give us minus 1/3, putting our constant out in front, e to the 2 theta cosine of 3 theta. That's u times v minus the integral of v du. Du is 2 e to the 2 theta. V is minus 1/3 cosine 3 theta. Well, typically when we integrate, we like to put the constants out front. There's a 2 and a minus 1/3. The negative and this negative make a plus. And we get 2/3, right? Putting our constants out in front. The integral e to the 2 theta cosine 3 theta d theta. But now we have, yet again, inside of our integration by parts problem, a problem we have to solve using integration by parts. This is going to be an integration by parts problem. And so we're going to take the same approach to solve this. We'll solve this one in blue. We're going to come off to the side. We're going to say, wonder who u is, and I wonder who dv is. U up here was e to the 2 theta, so we'll stick with that, e to the 2 theta. We know what du is going to be because we did e to the 2 theta. We took its derivative here, so we get 2 e to the 2 theta d theta. Now, dv, right? dv is going to be cosine 3 theta d theta. And we're going to use a similar approach. We knew how to integrate sine 3 theta by using this formula here. We're going to integrate cosine 3 theta by doing the same thing. So we're going to get, for v, we're going to get our 1/3. The integral of cosine is not negative, it's positive sine. So we're going to get sine 3 theta. And now when we go to write down our answer, right? When we write down our answer, we have equals, we have a negative 1/3 e to the 2 theta cosine 3 theta. That comes from here, straight down, plus 2/3. And then here, because this is integration by parts, we're going to have uv minus the integral of v du from our blue work off to the right-hand side. uv here is going to be 1/3 e to the 2 theta. Sorry, 1/3 times e to the 2 theta. So that's going to be 1/3 times e to the 2 theta times sine 3 theta. That's our uv minus, right? Minus, because we're doing integration by parts, minus the integral of v du. V du. Okay, when we take a look at v, we have a 1/3, so we'll put that out in front. The integral u is e to the 2 theta, v is sine 3 theta, so we get e to the 2 theta sine 3 theta d theta. And somehow or another, I lost this 2, didn't I? Because it's du, so I get 2. So I lost the 2, e to the 2 theta d theta. So there's also a 2 right there. All right, that helps. Because it's v is 1/3 sine 3 theta, 1/3 is there, sine 3 theta is there, times du is down here, so that's 2 times a third gives us 2/3, e to the 2 theta d theta. And we can close our bracket. Now, if we write this out, right, if we write out what we're looking at here, if we just simplify everything we have, what do we have now? We have minus 1/3 e to the 2 theta cosine 3 theta. 2/3 times 1/3 is going to be plus 2/9 e to the 2 theta sine 3 theta. Here we have 2/3 times negative 2/3. That's going to be minus 4/9. And then we're going to have the integral of e to the 2 theta sine 3 theta d theta. And if we take a look at our answer, so far so good, assuming I haven't made any silly algebra mistakes, which I'm prone to make. So if I've made one somewhere in there, I apologize. If we look at this and we gaze upon this term right here. This is where we begin when we're first learning the integration by parts process. We look at this and we ask ourselves, wait a minute, what am I doing here? It almost looks like I'm going in circles. Because we started with, our original problem was the integral of e to the 2 theta sine 3 theta d theta. That's exactly what we have shown back up over here on the far right-hand side. So what's our choice? Our choice is to do integration by parts here again. Well, that's not going to make any sense. That's not going to help us. Hopefully we can realize that's not going to help us. If we do that, we're going to generate a cosine term. We're going to generate a sine term. And then we're going to generate another integral, just like this one that we integrated up here. We're going to generate another integral with a cosine. And then when we do it again, because we're going to start doing it a 4th time, we're going to get back to another sine. This is just going to go in a circle. It's always going to circle back to an integral that looks just like this, i.e. it's always going to circle back to our original problem. Now, we looked at a problem like this in the lecture, and there's a problem like this in the reading. And what we do in this situation is we say, okay, I'm going to move this using my rules of algebra. I'm just going to move this over here. Over here, we have 9/9, right? We have 1, we have 9/9 right there. I'm going to move this over here. When I move negative 4/9 over here, I get 13/9, right? Because when I move a negative over here, it becomes positive 4, 9, 13. The integral of e to the 2 theta sine 3 theta d theta equals, throw our plus c out here, minus 1/3 e to the 2 theta cosine 3 theta plus 2/9 e to the 2 theta sine of 3 theta plus c. Now that's not what they asked us to find. They did not ask us to find 13/9 of this integral. The original problem was just find me that integral.
But we know how to turn 13/9 into 1. We multiply both sides by 9/13. So I'm going to multiply over here by 9/13. But if I do that, I have to multiply over here by 9/13. Over here, when I multiply by 9/13, I'm left with now just the integral of e to the 2 theta sine 3 theta d theta. Over here, I'm left with negative, right? Negative from here, because I'm going to have to distribute. I have a 3 and a 9, so that's going to be negative 3/13. There's 1 times 9 divided by 3 times 13. 3's cancel. E to the 2 theta cosine 3 theta plus, here, when I multiply by 9/13, the 9's cancel, and I get 2 over 13. E to the 2 theta sine 3 theta plus c prime. 9/13 of our previous c, or you could call it regular c. It's just a constant of integration. It represents all real numbers. You don't technically have to change your notation. If you called it c, I would be fine with that. Okay, so that's number 13. So I've done 4 and I've done 8 and I've done 13. All right. Let's skip down. Let me clean the whiteboard here. Let's skip down. We'll take a look at something like number 27. Okay. Now 27 is not an indefinite integral. It's a definite integral, i.e. it has upper and lower bounds, right? We're gonna have to evaluate it when we're done. So what do we have here? We have the on 27, we have the integral from root pi over 2 to root pi. We have theta cubed times cosine of theta squared d theta. Okay. So if we're going to do this problem, right, we look at this and we think to ourselves, well, this looks like an integration by parts problem. It has a power of our variable here, and it has a trig function next to it, and multiply together. That's reminiscent of what we've done previously with integration by parts. So if we just approach it like we've approached every other problem, right? We have theta cubed there for u, and then for dv, we're going to write cosine theta squared d theta, right? Cosine theta squared d theta. Now we know the game. The game is going to be to take the derivative here. That's going to be 3 theta squared d theta. And over here, we're going to have to integrate. Now, perhaps we're going to have to do a u sub because we have cosine theta squared, right? If we try to do that, we would say, well, we're going to let u equal theta squared. All right, we're going to let u equal theta squared. But then du is going to be 2 theta d theta, right? 2 theta d theta. And now when we go back and try to do our u sub, and we rewrite this, Sorry, I stopped the recording there because I had a barking dog. So when we come back and try to do our U sub here, right? If this was a typical U sub problem like we worked on back in section 5.5, we would say, okay, this is equal to the integral of cosine theta squared, which we're going to call U. But while we're going to call that U, and we're going to rewrite it like this, before we can write a du, we need a 2. Okay, we have a rule for that, right? We can put a 2 here and we put a half here. That was our section 5.5 U substitution. If you need a constant, just put 1 in. So we can do that. But the rest of du is d theta, which we have right here. But now we've reached a problem, right? In section 5.5, we said if you need a constant, like a 2, just put a 2 in and multiply by half on the outside. That's fine. You just multiply by 1, you haven't changed the problem. But you can't put in a function and then multiply by the reciprocal of the function outside. That's not allowed. I need a theta. I don't have a theta. But if we take a look at our original problem, we do have a theta. See, we have 3 thetas right here. There are 3 of them. There's theta cubed here. Some of us, when we were writing the problem down, maybe we asked ourselves, I wonder why there's a theta cubed here, but a theta squared here. Maybe that made us a little uncomfortable. Why is 1 cubed and 1 squared? Maybe not. Maybe we haven't done enough problems to notice things like that yet. But there's a hint in the fact that that's a cube and that's a square. See, over here, we need a theta right here. Well, we can't introduce a theta in the problem. But what we can do, right? What we can do is we can go back to our original problem where there were 3 thetas. Let's use 2 of them for du. Right? We use 2 of them. And if we use 2 of them for du, we have to account for all 3. So we'll put the third one right there. Theta squared times theta, theta cubed. That's what we started with. And now our integral has a theta right there. And our U sub works. And now 2 theta d theta turns out to be du. And so when we integrate, we get the integral of cosine is sine, so we get 1/2 sine. U is theta squared. And our integral works. See, we weren't short a theta. We just didn't use the thetas appropriately. We put all 3 of them for u, when what we needed to do was use 2 of them for u, save the third one for over here so that our U sub worked when we were calculating B. And now we know what B is. B is 1/2, right? The integral of this, we just integrated it right here. B is going to be 1/2 sine theta squared. And now we're ready to do our U substitution. So this integral turns into, remember, it's going to be UV minus the integral of V du. That's going to be then U times V. U times V is going to be 1/2 theta squared sine of theta squared, right? U times V minus the integral of V du. Well, that's going to be 1/2 times 2, Well, 1/2 times 2 is 1. Theta from here. Sine theta squared d theta. D theta from here. Well, you know, a funny thing, I think we know what the integral of theta, sine theta squared d theta is going to work out to be. Because we did essentially the same integral right here, other than we did it for cosine. Over here, we're going to do it for sine. We don't need to redo this u substitution. We don't need to come in here and change this to sine and change this to sine. And then say, well, when I change this to sine, it's going to be sine u du. And then say, well, when I integrate sine, I'm going to get a minus because the integral of sine is negative. And this is going to be cosine theta squared. So this turns out to be, if we do the problem, we don't even need a u sub here. This is just a straight section 5. Sorry, we don't need an integration by parts. This is just a straight section 5.6 u sub problem, 5.5 problem. So what do we have now? We have 1/2 theta squared sine of theta squared minus, and when we integrate this, we know what we're going to get the integral of sine is negative cosine, so those two negatives make a positive. We're going to get 1/2 from here. And then we get, instead of sine theta squared, we're going to get cosine theta squared. And we're going to evaluate that because it's a definite integral between the root of pi over 2 and the root of pi. And so now we have to do our fundamental theorem of calculus part 2 part, right? We got to do the fundamental theorem of calculus where we find the antiderivative evaluated at b minus the antiderivative evaluated at a. We found the antiderivatives, but now we have to go through and put all the messy things in there. So what is that going to look like? I don't know. Let's find out. It's going to be 1/2. We're going to put in the square root of pi. The square root of pi squared is just going to be pi. This is going to be sine of the square root of pi squared. Now, if we think back, because we haven't done this for this semester yet, this is the sine curve, right? This is pi. Well, the sine of pi is 0. So this is going to be sine root pi squared, or sine of pi. So that's going to be 0. Plus 1/2. And here we have cosine of pi. Right, cosine pi, because we have the root of pi squared, so that's going to be pi. Well, the graph of cosine, right, the graph of cosine looks like this. This is pi right here. So that's going to be cosine of pi, that's going to be -1. Minus, right, because we're doing the fundamental theorem of calculus, this is f of b minus f of a. So we have to evaluate it at the root of pi over 2. So this is going to be 1/2. The root of pi over 2 squared is going to be pi over 2. That's going to be sine of pi over 2. Well, pi over 2 is here. So sine of pi over 2 is +1, so that goes here. Plus 1/2. Cosine of pi over 2, because the root of pi over 2 squared is pi over 2. The root of pi over 2 squared is pi over 2. That's pi over 2. So cosine of pi over 2 is 0. So we have 1/2 times pi times 0, that's gone. Here we have -1/2, all right, -1/2. Here we have minus pi over 4, right? 1 times pi is pi, 2 times 2 is 4, so that's minus pi over 4. And here we have 1/2 times 0, which is 0. So we get -1/2 minus pi over 4. So what happened in this problem? Well, we're 27 problems into the homework. While we haven't done 27 problems because we didn't get all the problems assigned to us, we're 27 problems into the homework assignment. And Mr. Stewart thinks when you're 27 problems into a homework assignment, you're ready for a bump in the road. And the bump in the road he gave us was, in order to do dv and turn it into v, we had to integrate. And when we tried to integrate, we had to do a u sub. And when we tried to do the u sub, we were missing a theta.
but we weren't really missing a theta. We just misallocated our 3 thetas in the original problem. We put all 3 of them here for u, but because we needed one of them over here, we went back, changed this to theta, from theta cubed to theta squared, put a theta here, and it allowed the problem to fall right out. And then when we got to this step, that's a straight section 5.5 problem. That's Calc 1. That's not even a U sub problem. Okay, that's problem 27. All right, that's going to conclude the video. Your job is to work your way through the rest of the problems, right? These problems that I've solved for you here, the examples that I've done in class, and the examples that are in the textbook, along with anything else you can find on any other video on the internet, hopefully is going to be enough to get you to allow yourself to force yourself. Allow is not strong enough to force yourself to do the work to solve the rest of the problems. They're not going to be easy. They're not going to fall straight through. They're not going to be simple. They're going to take some thinking, some patience on your part. And that's what's supposed to happen. All right. So hopefully this gets you off and running on section 5.6. Everybody, I appreciate you coming by and watching the video.